We are in section 7.4 and we're continuing with pulse circuit response. Pulse circuit response is important to understand in digital applications, as these tend to use pulsed or rectangular waveforms. The wave shapes associated with sinusoidal waveforms is much different from that of rectangular. And so what we looked at in previous sections was we were considering a sinusoidal waveform looks kind of like this. Now we're going to be looking at a waveform that would look more like this, a rectangular or square wave. Sometimes we call them pulsed. RC time constants. RC time constants define the time it takes for a capacitor to charge. In the circuit below, we are charging the cap with a changing DC source, which effectively is notice a rectangular wave. And so here we have a circuit. We're applying a 12-volt DC source. Notice not sinusoidal. And here we have a switch. And so when the switch is in this position, the cap is charging, and there's going to be, we're talking about time, there's going to be a time associated with how long it takes this capacitor to charge. And then when the switch goes into this position, like it is over here, this is the same circuit, and when it goes into this position, now the applied voltage stops and now the capacitor is discharging. But effectively, this applying a voltage gives us our high and our square wave, and then when the switch closes we have this. So this would be indicating our square wave input. For a given cap size, it will take a certain amount of time for electrons to accumulate on the plates of the cap and fully charge, dependent upon the size of the cap and the charging current through the resistor. So in this particular case, here we have a voltage applied. There is a resistance here. This will allow a certain amount of current to flow, and then it will cause this capacitor to charge. The electrons are going to be flowing as such. They will charge this capacitor, and the polarity on the cap will be as such. And again, depending on how long the voltage is applied and how much current is flowed will affect how long it takes for this capacitor to actually charge. Let's see, dependent upon the size of the cap and the charging current through the resistor. Okay, the size of the resistor will greatly influence the time of the cap to charge. So the size of this resistor has a great deal to do with how long it will take this capacitor to charge. Now, let's continue with this discussion. This is the same circuit here. The value of charging current decays as the cap charges, and so let's again, here we have the voltage applied, and here this would be, here we'd have a minus, here we'd have a positive here, and as this switch is closed, current is flowing, and this capacitor is charging. Now what we'll notice here is that this capacitor is going to act much like a battery. And you'll notice that the positive terminal is here, the negative terminal is here, and the charging of this cap is going to oppose this charging voltage. And so when this capacitor is fully charged, what will happen is that this will completely oppose this, and effectively no current will be flowing. And so what this is saying, the value of charging current decays. It decays as the cap charges. So initially, as this switch is closed like this, there's a lot of current that is charging this cap, but as this cap reaches its full charge point, then current decreases and there is effectively no current flow. The charge in the cap will oppose the DC source. Recall, when the cap is fully charged, current will cease to flow. Okay? The time required for the cap to charge is divided into 5 periods and called time constants, and we're going to be looking at it in the next 2 screens. Before we go there, though, let's take a look at this particular schematic. Notice when the switch is closed, now the voltage is no longer applied, so the applied voltage, you'd have something like this. At this point, we've got no voltage applied. But in this case, the circuit is closed, and now there is a discharge path for the capacitor. Now notice something, that in this case, the current path was like this as it was charging, okay, in this direction. But when this switch is closed, notice it's a negative to positive, the current is going to reverse and it's going to flow in the other direction until this capacitor charges, and then if we close the switch again, then it would recharge again. Okay, time constants. The Greek letter tau is used to represent one time constant. And here we have tau equals, and notice R times C. And the formula above is used to calculate time constants, and this is in relation to how long it takes for the capacitor charge, which we had looked at in the previous screen. Now here we have a graph. This diagram, the diagram below, shows the cap charging in comparison to charging current. So notice, what are we looking at here? Here we have the line going up here, and this is a capacitor, and we are charging the capacitor, and this is the voltage, and this is the current related to this charge. And these letters down here, these represent the time constants, tau, which we just mentioned on the previous slide. After one time constant, the cap is charged to 63.2% of the applied voltage, and the charging current has decreased to 36.8%. So what does this mean? Well, here at 100%, what we're looking at, this is the applied voltage, but it is also the applied current, and this would have to do with the size of the resistor that we were looking at previously. And so here we have, initially when that switch is closed, we have massive current flowing through the, well, I shouldn't say massive, but we have a lot of current flowing through the resistor, and the capacitor is beginning to charge. And what we'll notice is that at 63.2%, the voltage on the cap, the voltage on the cap will be 63.2% of the applied voltage, and this is that. This is the first time. This would be time constant 1, if you will, right here. And you'll notice that the charging current has decayed to 36.8% of its original value. During the next time constant, the cap will charge an additional 63.2% of the remaining voltage. Okay, and the current will decrease likewise. Okay, what does that mean? Well, here we're at 63.2% of the applied voltage, and now the difference between 63.2% is a given value, and this cap will charge to 63.2% of that value, of what is left over between here and the applied value. And it will continue to do this through 5 time constants, and the current will be decreasing at the same ratio. Now, after 5 time constants, the cap will be at 99% of its value, and the current will decrease to less than 1% of its initial value. And this is much like we looked at in that previous circuit where the capacitor was charging, and when it reached its full charge, it was opposing the applied voltage, and current ceased to flow. Okay, the below chart illustrates the capacitor current and voltage during discharge. Okay, so in this particular screen, we're looking at the voltage and current during charging. Now we're looking at the voltage and current during the discharge time. You'll notice here the DC and I are going to be proportional. Now in this case, this would be the capacitor where the switch is now in the position where the cap can discharge through the resistor, and the voltage and current will be directly proportional because now the capacitor is in effect the battery, and it is providing all of the voltage and current for the circuit, and so they will decrease. And you'll notice here during time constant 1, the voltage will decrease by 63.2% of its value. And notice that up here we're saying the time 0 is at 100%. It begins to discharge. At time 1, it's down to 36.8%. And it will continue to decrease by 63 of the remaining voltage until the 5 time constants have elapsed. So this is again going to be the same relationship as we saw in charging, only now the voltage and current are deteriorating, and it's going to be in relationship to the same time constants that it charged by. Okay, solve. RC time constant for the below circuit. So here we have a circuit, and let's find our little calculator, and let's do a little bit of calculating here. First of all, here we have the applied voltage 100 volts. Here we have a switch, and here we have a resistor and a capacitor. Now our calculation for the time constant is going to be R times C. So let's go over here, and our R value is 2.2 megs, so 2.2 exponent 6 times the value of 500, and this will be exponent minus 6, and that will equal, and we have a value here of 1,100, so we're saying 1,100 watt. Well, those are seconds, and so let's go and let's divide that by 60, and we'll say, okay, so this actually has a charging time of 18⅓ minutes. So if we were to close this switch, it would take 18.3 minutes for this cap to charge. Now this is a fairly long charge time, but that is greatly impacted by the size of this. If this was a much smaller resistor, that charge time would be greatly reduced. Now, if we're looking at for it to be fully charged, it would be 5 times this value. So if we took that times 5, we'd be looking at, an hour and a half for this to be fully charged, and again an hour and a half for it to be fully discharged. Okay, RL time constants, we're not going to spend any time with these, but I'm just going to mention them. The RL circuits also have a time constant computed thusly, and here we're going to have tau equals L. Now notice it's L divided by R. In our RC, it was R times C, and so the tau here will be probably a pretty small value, because inductance is typically a value less than 1, and our resistance is, if it's 1,000 or 1,000,000 or whatever, we're going to find that the time constant here will be very short. Okay, in this section we looked at time constants. We solved for a time constant in this particular circuit. We looked at the discharge time, and they were based on time constants. We looked at the charge time based on time constants, and remember that the voltage and current were inversely proportional during charge, and they were directly proportional during discharge. We looked at, okay, here is tau. And we looked at, and remember this was, in this particular section, we're looking at time constants, and we're relating them directly to a rectangular wave, vice the sinusoidal wave that we had looked at in the previous sections.